Think for a second about just the sheer volume of data zipping around inside your phone or computer.
Mm-hmm.
It's happening at speeds that are, well, almost impossible to really grasp.
It really is staggering.
And the main language, the thing enabling all this high-speed internal chat, and it stretches way beyond our PCs, right? Into data centers, AI stuff, even cars now,
Everywhere.
is PCIe, Peripheral Component Interconnect Express. It basically took over from the older, slower, parallel ways of connecting things. It's truly the backbone now.
Absolutely. And what's just, immediately striking is how fast it's evolved. The pace of innovation is relentless.
Right.
We've seen it jump from an initial 2.5 gigatransfers per second all the way up to the latest 64 GTs. Each new generation pretty much doubling the speed.
Doubling. But getting there wasn't simple, I take it.
Oh, definitely not straightforward. Engineers have had to constantly tackle some pretty significant hurdles, especially making sure those super fast signals actually arrive intact. Signal integrity is a huge challenge.
Exactly. So that's what we're diving into today. We're going under the hood, looking at the electrical foundations of PCIe, the physical layer, the stuff that makes all that speed possible.
And nuts and bolts.
Yeah. We've got some pretty dense technical documents here, specification details, that kind of thing. Our mission really is to pull off the most critical and, frankly, the most interesting electrical ideas that let PCIe work and keep scaling up.
Kind of decoding the magic behind the speed.
Consider this your express lane to understanding a really vital bit of modern tech. Okay, let's unpack this. Starting with, well, the basics. The speeds themselves, data rates, and how they actually encode that data onto the wires.
Sounds good. And the data rate story itself is pretty compelling. You mentioned 2.5 GTs for Gen 1.x. Then it doubled to 5.0 for 2.x Gen 3, brought 8.0 GTs, then 16.0 for Gen 4, 32.0 for Gen 5, and now Gen 6 hitting that remarkable 64.0 GTs.
Each step basically a doubling.
Pretty much. And that doubling was really critically enabled by, smarter and smarter ways of encoding the data electrically.
Right. So back in the Gen 1 and Gen 2 days, they used something called 8B10B encoding. Let's break that down. Sounds like extra bits.
That's exactly it. For every 8 bits of actual data you wanted to send, they transmitted 10 bits over the wire.
Okay, so that's 20% overhead. Why bother with the extra baggage?
It seems like waste, but it was vital. 2 main reasons. First, it guaranteed something called DC balance. Basically, preventing a buildup of voltage on the lines over time, which could mess up the signal.
Ah, okay, like static.
Sort of. And second, those extra bits ensured there were always enough transitions changes from high to low or low to high voltage in the signal stream. The receiver uses those transitions to lock onto the timing, to recover the clock signal from the data itself.
So a receiver can stay synchronized.
Precisely. So take Gen 2 at 5.0 GTs. With that 20% overhead, the actual usable data rate per lane, one direction, was 4 gigabits per second. It's a trade-off, right? You sacrifice a bit of raw bandwidth for reliability.
That makes sense, like adding some extra framing to make sure the message gets through clearly. But then Gen 3 arrives and things get way more efficient.
Way more efficient. Gen 3 and then Gen 4 and Gen 5 after it, they switched to a 128B, 130B encoding.
Okay, different numbers.
Yeah. Here, for every 128 bits of data, they only added a tiny 2-bit header for synchronization. Overhead dropped dramatically, down to about 1.5%.
Wow, that's a huge difference.
It is. And they also brought in data scrambling techniques, basically mixing up the data patterns to ensure enough transitions and keep that DC balance without needing all those extra overhead bits like 8B10B.
Clever.
And what's really neat is that Gen 3, running at 8.0 GTs, almost doubled the effective bandwidth compared to Gen 2, but didn't need to double the actual signaling speed on the wire. It was just a much smarter way to use the bandwidth they had.
Okay, so smarter encoding lets them pack more useful data into the same electrical space. But then we get to Gen 6, 64 GTs, and a totally different approach. PM4, what's that about?
Yeah, Gen 6 was a big shift. Pushing to 64 GTs required introducing PM4, that's pulse amplitude modulation, with 4 levels.
4 levels, okay.
Think of the older way, NRZ, non-return to 0. It's like a basic light switch, either fully on for a 1 or fully off for a 0. 2 levels.
Simple enough.
PM4, though, it's more like a dimmer switch with 4 distinct brightness levels. And the key is, with 4 distinct voltage levels, you can encode 2 bits of information in the same time slot, the same symbol period.
Oh, okay. 2 bits per symbol instead of 1.
Exactly. So compared to Gen 5's 32 GT's NRZ signal, PM4 effectively doubles the raw data rate, gets you to 64 GTs without having to double the fundamental frequency, the bandwidth needed on the wire. It's very efficient data-wise.
That sounds, well, almost too good to be true. Doubling the data rate in the same bandwidth, what's the catch? 4 levels must be harder to distinguish than 2.
That's precisely the challenge. The main trade-off is a big reduction in the voltage difference between those adjacent levels. Think about that dimmer switch again. The more steps you add, the smaller the change between each step.
Right. Finer adjustments.
So technically, we talk about the eye height. It's a measure of signal clarity you see on an oscilloscope. For Gen 6 TAM4, that eye height can be incredibly small, maybe as little as 6 millivolts between levels.
6 millivolts. That's tiny. How does that compare to before?
Well, Gen 5 NRZ, you might have had around 15 millivolts or so for the whole eye opening. So this much smaller vertical opening makes the PM4 signal way more vulnerable to noise.
Okay, that makes sense.
It means a higher inherent bit error rate, more chance of the receiver misinterpreting a level. It's like trying to hear someone whispering very subtle differences in tone across a noisy room, much harder than just hearing loud on or off.
So they get the speed, but the signal's walking a tightrope. How do they compensate for that higher error rate? You can't just accept more errors.
No, absolutely not. Gen 6 had to build in several countermeasures. A big one is lightweight forward error correction, or FEC.
FEC, data direct encodes.
Yep. It adds some redundant information to the data stream. The receiver can use this extra info to detect and actually correct a certain number of errors on the fly.
Okay. Fixes errors automatically.
Within limits, yes. They also use things like CRC cyclic redundancy check, which is very good at detecting if errors happened, even if FEC couldn't fix them. And they moved to something called FLIT-based encoding, which helps manage the data flow and deal with the extra latency that FEC introduces.
So PM4 Speed Boost came packaged with a mandatory error handling toolkit.
You got it. The encoding advancements, especially PM4, were essential to keep pushing bandwidth. But it wasn't a free lunch. It demanded much more sophisticated error management.
Okay, that provides a great picture of the encoding evolution.
Okay.
Now, how do these signals actually travel physically? You mentioned differential signaling earlier. What's the core idea there?
Right. Differential signaling is fundamental to high-speed links like PCIe. Instead of sending a signal on one wire relative to ground, you use a pair of wires, usually called D plus and D.
Plus and minus.
Exactly. The transmitter drives them with opposite polarity signals. So a logical one might be when D plus voltage is higher than D, and a 0 is when D voltage is higher than D plus E. The key is the receiver only cares about the difference in voltage between those two lines.
And why do it that way? What's the big advantage?
Noise immunity. By
By
far the biggest advantage. Think about electrical noise from outside interference, crosstalk from other signals.
Something you don't want.
Right. Because those two wires, D plus and D, are routed really close together, usually twisted or carefully laid out on the PCB. Any external noise tends to hit both wires almost identically. We call that common mode noise.
Okay, so noise hits both wires.
And since the receiver is only looking at the difference between D plus and D, that common noise, which affects both equally, gets subtracted out. It just cancels.
Ah, brilliant. Like noise-canceling headphones, but for data signals.
Exactly like that. It makes the link much more robust against interference. Plus, there's another benefit. The opposing signals create electromagnetic fields that tend to cancel each other out too, which reduces the EMI emitted by the PCIe link itself.
So it's quieter electrically, both incoming and outgoing. What about AC coupling? I sometimes see capacitors mentioned with differential pairs.
Good point. Often the transmitter and receiver are DC isolated, using small capacitors placed in series, usually on the transmitter side of the D plus and D lines.
Why isolate them?
It allows the transmitter chip and the receiver chip to operate with slightly different DC voltage levels, their own sort of ground reference or common mode voltage. The spec allows this common mode voltage, VCM, to be anywhere between 0 and 3.6 volts. AC coupling lets the high-frequency signal pass through but blocks any DC difference.
Flexibility in design.
Yep. But choosing the right capacitors and placing them carefully is critical. You don't want them adding unwanted signal distortion or reflections. So yeah, differential signaling, often with AC coupling, is really a cornerstone for making these high-speed links work reliably in noisy real-world systems.
Okay, so we have these efficient noise-resistant signals. What about their actual strength, the voltage levels? Were they big signals or tiny ones?
Well, the specification defines the differential voltage swing right at the transmitter VTX DIFFPP, peak to peak. For the early generations, Gen 1, Gen 2, Gen 3, the nominal range was generally between 800 millivolts and 1200 millivolts. Peak-to-peak difference.
Okay, so around 1 volt, give or take.
Yeah.
Seems reasonably strong.
It was enough to survive the channel losses back then and still be detected reliably.
Did that change much with the faster generations, Gen 4 and Gen 5?
The specs got a bit tighter, more precisely defined to handle the higher frequencies. Gen 5, for instance, had a maximum peak-to-peak differential voltage of 1300 millivolts, so slightly higher potentially. They also defined other parameters like the voltage during specific sequences, like the electrical idle exit, around 250 millivolts for that one. But the really dramatic change, again, was Gen 6 with PM4.
Because of those 4 levels being squeezed in.
Exactly. As we said, that vertical eye opening shrunk massively. That effective signal difference between levels, the eye height, could be down to just 6 millivolts.
6 millivolts again. That's just, wow.
It really is. And that tiny margin means you need incredibly sensitive receivers. Plus, testing and measuring these signals accurately requires highly specialized, precise equipment. It's also worth noting that peak-to-peak voltage spec. It's not something you just stick an oscilloscope probe on and read directly. It's actually a value calculated after the receiver does its clock recovery, using specific algorithms defined in the standard.
So even measuring it is complex. That 6 milliV figure really drives home the engineering challenge at these speeds.
Oh, okay.
So we're sending these tiny, carefully encoded differential signals. But what happens when they actually travel through the physical path? The PCB traces, the connectors, maybe cables, they can't arrive perfectly clean, right?
Oh, absolutely not. They get pretty beaten up on the journey. As these high-frequency signals travel through the physical channel, the copper traces on the board, the pins and connectors, any cables involved, they suffer significant degradation.
Beaten up how? What causes the damage?
It's mainly down to two things. Frequency-dependent losses, meaning higher frequencies lose more signal strength than lower frequencies, and impedance discontinuities, which cause reflection.
Okay, let's take the losses first. I hear about skin effect. What's that?
Right. At high frequencies, electrical current doesn't like to flow through the whole bulk of a copper wire or trace. It tends to concentrate near the surface, the skin. This effectively reduces the cross-sectional area the current can use, which increases the resistance for those high-frequency components, leading to more signal loss. And this loss gets worse proportionally to the square root of the frequency. So faster signals suffer more.
Got it. More speed, more skin effect loss. What about dielectric loss?
That happens in the insulating material between the copper traces the PCB material itself, like FR4. As the signal's electromagnetic field passes through this dielectric, some energy gets absorbed by the material, basically turning into heat.
Like microwave cooking, but tiny.
Kind of. And this loss is directly proportional to the frequency. So double the frequency, double the dielectric loss. At the multi-gigahertz speeds of modern PCIe, this becomes a really dominant loss factor.
Okay, so skin effect and dielectric loss both chew away more at the high frequencies. And then you mentioned reflections. Sounds like signal echoes.
That's a great way to think of it. Reflections occur whenever the signal hits a point where the electrical impedance changes abruptly.
Impedance. Like electrical resistance, but for AC signals.
Roughly, yes. Think of it as the opposition the signal sees. If that opposition changes suddenly, maybe where a trace goes through a via, a hole connecting PCB layers, or at a connector, or even just where a trace width changes slightly, some of the signal's energy bounces back.
Like light hitting a mirror.
Exactly. And these reflected bits of signal can travel back and interfere with the following bits that are still coming down the line. This interference between symbols, between bits, is called intersymbol interference, or ISI. It basically smears the data out, making it harder to read.
So putting it all together, these channel effects preferentially kill off the high-frequency parts of the signal and cause echoes that blur the data bits together. That must make the receiver's job incredibly hard, especially at Gen 5 or Gen 6 speeds.
You got it. These effects distort the nice, clean square waves you started with, shrinking and blurring the data eye at the receiver. If it gets bad enough, the eye closes completely, and you can't tell a 1 from a 0 reliably. That's why signal conditioning is absolutely essential.
Right, the countermeasures. How do they fight back against this channel degradation? Let's start with the early days again, Gen 1 and Gen 2. They used de-emphasis. How did that help?
De-emphasis was a fairly simple form of transmitter equalization, TX-EQ. The basic idea was to pre-distort the signal at the transmitter to counteract the channel's high-frequency loss.
Pre-distort? How?
Specifically, after the signal voltage changes, a transition, If the next bit is the same as the previous one, representing a lower frequency component, the transmitter would deliberately send it out at a slightly reduced amplitude.
Okay.
But the very first bit right after a transition, which carries more of those important high-frequency details, that one gets sent at full strength.
So you're basically boosting the transitions relative to the steady level.
Exactly. You're de-emphasizing the parts of the signal that the channel doesn't attenuate as much. It's a static preemptive adjustment. For Gen 1, there was a standard level, magically 3.5 decibels dB. Gen 2 added another option, make it a 6.0 dB, giving a little more adjustment.
Was it effective?
It worked reasonably well for the typical channel lengths of the time, maybe 20 inches of standard FR4 PCB plus a couple of connectors, but it was fixed, not adaptive. For longer channels or as speeds increased, it just wasn't powerful enough. Sometimes you needed special repeater chips with stronger, non-standard equalization, even back then.
Okay, so de-emphasis was step 1, but pretty limited. Gen 3 and onwards needed much bigger guns, right? Real equalization involving both ends.
Absolutely. For Gen 3, Gen 4, Gen 5, and now Gen 6, much more sophisticated and adaptive equalization, using both the transmitter, TX, and receiver, RX, became mandatory.
And the main goal is still the same, to undo the channel damage.
Exactly. The goal is to effectively create an inverse filter to the channel response, compensate for the losses and distortions, open that data eye back up at the receiver, and get reliable detection.
Let's look at the transmitter side first. TXEQ. I saw the term feed-forward equalizer, FFE. What is that?
An FFE is essentially a digital filter built into the transmitter's output stage. It works by adjusting the amplitude of the signal being sent based not just on the current bit, but also on the bits that came before it and the bits coming after it.
Based on neighbors. How?
It uses adjustable taps. There's the main cursor tap for the current bit. Then precursor taps look at upcoming bits and can boost the signal before a transition. That's called pre-emphasis. And post-cursor taps look at past bits and can reduce the signal amplitude after a transition similar to de-emphasis, but more flexible.
So it shapes the outgoing wave very precisely based on the data pattern.
Exactly. By carefully setting the weights or coefficients for each of these taps, the transmitter can sculpt the waveform to better survive the specific channel it's driving.
How many taps are we talking? Has that changed over the generations?
For Gen 3, 4, and 5, a 3-tap FFE was common, usually one precursor, the main cursor, and one post-cursor, with PM4 and Gen 6 being much trickier.
Right, more sensitive to ISI.
They typically move to a 4-tap FFE, likely something like 2 precursor taps, often called pre-shoot, the cursor, and 1 post-cursor de-emphasis tap. More taps give finer control.
Okay. And what about presets? I saw those mentioned for TXEQ.
Ah, yes. Presets are standardized combinations of these FME tap coefficients. Think of them like predefined EQ settings on a stereo. Gen 3, 4, and 5 defined 11 standard ones, P0 through P10.
Why have standard settings?
It really simplifies the initial link bring-up, the training process. Instead of trying countless combinations, the transmitter can ask the receiver, hey, try preset P5, how does that look? The receiver evaluates the signal quality and tells the transmitter which preset works best as a starting point. It speeds things up, and for compliance testing, devices have to prove they work correctly with all the required presets.
Got it. A quick way to find a decent starting point. Okay, so the transmitter shapes the signal. What about the receiver? RX EQ must be just as important, if not more so.
Oh, absolutely critical, especially at the higher speeds where the signal arriving can be pretty messy. The receiver typically employs 2 main techniques, CTLE and DFE.
Let's take CTLE first. Continuous time linear equalizer. What does it do?
CTLE is essentially an analog filter. Its job is to provide frequency-dependent gain. It typically cuts the lower frequency components of the incoming signal and boosts the higher frequencies, especially around the Nyquist frequency, half the data rate.
So it does the opposite of the channel. The channel cuts highs, CTLE boosts them.
Exactly. It helps counteract that low-pass filtering effect of the channel. The main goal is to open up the vertical dimension of the data eye, making the voltage levels easier to distinguish again.
And have these CTLE filters gotten more complex over time, like the TX FFEs?
Definitely.
Nah.
To handle the increasing channel loss at higher speeds, the reference CTLE designs and the specs have become more sophisticated. Gen 3 might have had a simple first-order filter, maybe a 6 to 9 to 12 dB gain range. Gen 4 moved to maybe a 2-pole, 1-0 filter, different gain range. Gen 5 uses something even more complex, like a 4-pole 2-0 filter, maybe -5 to -15 dB gain.
More poles and zeros means more control over the frequency shaping.
Precisely. Like having more bands on a graphic equalizer, it allows for finer tuning to match and compensate for more complex channel characteristics.
Okay, that's CTLE boosting the highs. What about the other one? DFE, decision feedback equalizer. Sounds different.
It is different. DFE is a nonlinear technique. It works after the receiver has made a decision about a bit, decided if it was a 1 or a 0.
Okay, after the decision.
Yes. It uses those decided bits to predict the interference, the ISI, that those previous bits are likely causing on the current bit being received. Then it subtracts that predicted interference before making the decision on the current bit.
Whoa, okay. It uses past decisions to clean up the present, like predicting echoes.
Exactly. It's particularly good at removing post-cursor ISI, the echoes from previous bits, often caused by those reflections we talked about. It helps clean up the horizontal dimension of the eye, reducing timing jitter.
And how many past bits does it look at? Have the DFE taps increased too?
Generally, yes. Gen 3 might have used just a 1-tap DFE. Gen 4 typically moved to 2 taps. Gen 5 often uses 3 or more taps. Gen 6 continues to use both CTLE and DFE, though the exact implementations can vary between chip vendors. More taps let it cancel out ISI from further back in the past.
So TXEQ shapes the signal going out, RxCTLE boosts the frequencies coming in, and RxDFE cancels out the echoes based on past data. It sounds like these need to work together perfectly. How do they get tuned? It can't be static like the old de-emphasis.
You're absolutely right. It's a highly dynamic and cooperative process. This happens during a specific state in that link training state machine, the LTSSM, called the recovery state.
Recovery. That's where the magic happens.
A lot of it, yes. When the link enters recovery, maybe to change speeds or just optimize the connection, the two devices negotiate their equalization settings. It's a back-and-forth conversation.
What does that negotiation look like?
It typically goes in phases. First, they might exchange capabilities, maybe try out those TX presets we mentioned. Then it gets more detailed. One receiver can actually tell the other device's transmitter, okay, tweak your precursor tap up a bit and your post-cursor down.
Seriously? The receiver coaches the other guy's transmitter.
Yep. The receiver knows what kind of signal it's seeing after the channel, so it's best placed to figure out what kind of precompensation is needed at the transmitter. This happens in both directions until both receivers are happy with the signal quality they're getting.
Happy meaning? What's the target?
They're aiming for a very low bit error rate, maybe better than 1 error in 1012 bits, 1 trillion, before even applying that forward error correction we talked about for Gen 6. Once they achieve that stable, clean link, they can transition to El Linero, the active data state.
That dynamic adaptation is incredible. And you mentioned the channel loss can be huge, like 36 dBs for Gen 5.
Yeah, 36 dB loss at the Nyquist frequency. 16 gigahertz for Gen 5. That means only about 2% of the original signal amplitude might actually reach the receiver.
2%? It's amazing it works at all. It really underscores how critical this whole dynamic equalization dance is.
It's the key to making those speeds achievable over real-world distances.
Okay, so the LTSSM orchestrates this equalization in the recovery state. What about the other states? You mentioned it manages the whole link life cycle. Let's walk through the main ones electrically. What happens right at the start in detect?
Detect is the very first state after, say, power on or reset. The PHY, the physical layer chip, isn't sending data yet. It's just listening, or rather probing electrically. It periodically sends out small signals to see if there's a valid receiver termination detected at the other end of the expected lanes.
Like checking if someone picked up the phone.
Kinda, yeah. Just checking for electrical presence, no high-speed signals yet. If it detects that termination, it moves on to polling.
Okay, polling. What's happening electrically there?
In polling, things start waking up. The transmitters start sending out special patterns called training sets, TS1 and TS2 ordered sets. This is the first real signaling. It tells the other side, I'm here, and helps establish basic communication. This is when the link exits the low-power electrical idle state. Sometimes devices might also send out specific compliance patterns here for testing.
Got it. Waking up and saying hello. Then configuration.
Configuration is where they negotiate the details. How many lanes will we actually use for this link width? How do we number these lanes logically? They also perform lane-to-lane deskew, making sure data arrives across all active lanes at the same time, compensating for tiny length differences in the wiring. And they check if any lane pairs are accidentally swapped, polarity inversion, and fix it. So active high-speed signaling is happening now on all the lanes they've agreed to use.
Setting up the highway. And then finally, L0. That's full speed ahead.
Exactly. L0 is the normal, active data transfer state. This is where the real work happens, sending and receiving the actual data packets. TLPs for user data, DLLPs for link management. Everything's powered up, full speed, consuming its normal operating power.
And recovery, we already touched on that. It's for retraining, speed changes, or rerunning that equalization process using those training sets again, then back to L0 if successful.
Correct. It's the state for reoptimizing the link.
Okay, those cover the active side. But power saving is huge these days. Let's talk about the low power L states. What's L0Os? Sounds like a light nap.
L0 subs, yeah, it's a very light standby. A transmitter can just decide to enter L0s on its own if it hasn't got any data to send for a moment. Critically, the receiver on the other end stays fully awake and ready.
So only the transmitter takes a break.
Per direction, yes. One direction can be in L0s while the other is still blasting data in L0. The power saving is minimal, but the big advantage is the exit latency is incredibly fast, nanoseconds, almost instant wake up.
Okay, barely noticeable. What about L1, deeper sleep?
L1 is a lower power state that both sides have to agree to enter. It's negotiated. When they go into L1, typically both the transmitter and receiver circuits powered down significantly or go into very low power modes.
Both sides this time.
Yes. Usually the main reference clock signal stays active to allow for a quicker wake up, although there's an option, using a side signal called CLKREQ chuck, to turn the clock off too for even more savings. Exit latency here is longer microseconds range, but the power savings are much more substantial than L0s.
Microseconds.
Yeah.
So pretty fast. Then I saw these L1 substates. L1.1 and L1.2. Why did they need even more variations of L1?
These were driven largely by the needs of mobile devices, laptops, tablets needing much better battery life than traditional L1 offered, but without the very long wake-up times of even deeper sleep states. L1.1 and L1.2 provide much lower power consumption than legacy L1.
How do they work electrically?
Both L1.1 and L1.2 rely on that CLKREQ shag signal being used by both sides to coordinate entry and exit. In both these states, the core high-speed PHY stuff, the PLLs generating the clocks, the transmitters, the receivers, they all get completely powered down.
Okay, main engine's off. What's the difference between L1.1 and L1.2 then?
Power versus latency, again, L1.1 gets you significant power reduction, maybe down to tens of milliwatts from hundreds for a PCIe 4.0x4 link. In L1.1, they power down the PHY, but they keep a small circuit active to maintain the correct DC common mode voltage on the signal lines.
Keeps the lines ready.
Right. So the exit latency is longer than L1, but faster than L1.2. Now, L1.2 is the most aggressive. It goes for near zero active power, maybe just 2 or 3 milliwatts for that same by 4 link. To get that low, it turns off everything, including the common mode voltage keepers.
Okay, total shutdown almost.
Pretty much.
No.
The penalty is the longest exit latency of the L1 family, because when it wakes up, it first has to reestablish that common mode voltage before it can even think about starting the high-speed signaling sequence.
Makes sense. So L1 substates offer this crucial middle ground, much better power saving than L1, essential for mobile, but faster wake up than the really deep sleep states like L2.
Exactly. L2 is often called sleep or L2, L3 ready. Here, main power rails might be off. Maybe just an auxiliary voltage stays on for wake up signals. The link is electrically off. Exit latency is very long, milliseconds. It's often a preparatory state before potentially removing main power completely in L3. Off.
Okay, so a clear ladder of power states, each trading deeper savings for longer wake-up times. Fascinating. Let's shift to the last major electrical piece, timing and reference clocks. This sounds absolutely fundamental. You can't have high-speed communication without precise timing.
You absolutely cannot. Stable, accurate timing references are the heartbeat of any synchronous serial link like PCIe. The spec is very strict about the reference clock, the ref clock.
What are the key ref flick requirements?
Standard frequency is 100 megahertz. Now, internally, a chip might use different frequencies, but the PCIe interface itself relies on that 100 megahertz reference. Frequency stability is key how much it's allowed to drift. For Gen 1 through Gen 4, it was plus or minus 300 parts per million ppm.
Tiny variations.
Tiny, but important. For Gen 5, they tightened that further to 100 ppm. The signal itself is usually differential, often using HCSL logic, though other formats exist. And crucially, there are very strict limits on jitter, those tiny timing variations on the clock edges. Low jitter is critical, and the exact requirements depend on the PCIe generation and the clocking architecture being used.
Okay, stable 100 megahertz, low jitter. I also saw a spread spectrum clocking, SSC. What's that for? Sounds like something you do to hide a signal.
Hey, not quite hide it, but spread it out. SSC is an optional feature, and its main purpose is to reduce electromagnetic interference EMI.
Noise reduction again, but this time noise going out.
Exactly. High-speed clocks and data signals create sharp peaks of energy at their fundamental frequency and its harmonics. These peaks can radiate and potentially interfere with other electronics or fail regulatory emission limits.
So how does SSC help?
It intentionally modulates or dithers the clock frequency slightly over time. Instead of a fixed 100 millihertz, the frequency wobbles a bit. For PCIe, it's typically downspread, meaning the frequency is modulated downwards from 100 millihertz by up to 0.5%, which is 5,000 ppm.
Wobbling the frequency. How does that reduce EMI?
Usually it's done with a slow triangular wave modulation, maybe around 33 kilohertz. By constantly changing the frequency, you spread that concentrated clock energy over a wider frequency band. The peak energy level at any single frequency goes down significantly, even though the total energy is the same. Lower peaks mean less EMI.
Clever trick.
Yeah.
But does intentionally messing with the clock frequency cause any problems?
Yes, there's a major impact. By definition, SSC introduces a lot of low-frequency jitter. That 5,000 ppm frequency variation is jitter from the receiver's perspective. This makes the receiver's clock data recovery, CDR, job much harder. The CDR circuitry needs to track data coming in based on a clock that's constantly sweeping up and down in frequency. It requires a much more robust CDR design that can handle this large, slow wander.
So reduced EMI comes at the cost of a more complex and tolerant receiver. Another trade-off.
Always trade-offs.
Okay, so we have the ref clock, maybe it was SSC. How is this clock actually distributed in a system? I saw three main ways. Common ref clock, SRNS, and SRIS.
Right, these are the main clocking architectures, and choosing between them is a big system design decision. Let's start with common ref clock, or CC.
Common meaning, shared.
Exactly. Both devices at either end of a PCIe link share the very same physical 100 millihertz ref clock source. One clock generator feeds both chips.
What's the advantage of that?
Simplicity for the receiver CDR. Since both ends are running off the same clock, there's very little frequency difference between them, just the inherent tiny instability, like that 300 ppm. The CDR doesn't have to work as hard to track frequency drift. Also, CC naturally supports SSC because both ends see the same frequency wobble. In fact, CC is mandatory for standard plug-in cards, like graphics cards, CEM spec.
Sounds good. What's the downside?
The clock distribution itself. You have to route that single clock signal very carefully across the motherboard or system to both devices, ensuring it arrives with very little timing difference, or skew the spec often requires less than 12 nanoseconds difference. That can be complex and expensive, especially on large boards with many devices.
Okay, so CC is simple for the PHYs but complex for the board layout. What about separate ref clock, no spread, SRNS?
SRNS means each device uses its own independent 100 megahertz ref clock source. And as the name says, no-spread SSC is not used in this mode.
Independent clocks, what's the benefit?
It completely eliminates that complex, low-skew clock routing problem. Each device just needs its own local clock source. Much simpler board design, potentially lower cost.
Sounds easier.
The catch. The catch is now the receiver CDR has to handle the full potential frequency difference between two independent clocks. That could be 600 ppm total for older gens, 300 ppm per clock.
So the CDR needs to be more robust.
Yes. It needs a wider tracking range. Receivers in SRNS mode also need elastic buffers to absorb the timing differences, and they use special SKP ordered sets, basically skip symbols that are periodically inserted or deleted to prevent the buffer from overflowing or underflowing due to the frequency mismatch. And of course, you lose the EMI benefit of SSC.
Okay, simpler board, harder CDR, no SSC. What about the third one? Separate ref clock, independent SSC, SRES. Sounds like a mouthful.
It is. SRAS tries to get the best of both worlds, sort of. Like SRNS, each device has its own independent 100 megahertz ref clock. But with SRAS, each device can also independently enable and use spread spectrum clocking.
Ah, separate clocks with SSC allowed on each. When did this come in?
It got formally added around the PCIe 4.0 spec time. The big advantage is you get the simpler clock routing of SRNS and the EMI reduction benefits of SSC. This is really appealing for things like external PCIe devices connected via cables, where routing a clean common clock over a cable is very difficult, but you still want EMI reduction.
Okay, seems ideal. What's the really big catch here?
It's the absolute nightmare scenario for the receiver CDR.
Worse than SRNS.
Oh, yes. The CDR now has to tolerate the combined worst-case frequency offset. That includes the base 300 ppm or a 100 ppm for Gen 5 plus, difference between the two independent clocks, plus the independent 5000 ppm swing from each side's SSC modulation, potentially going in opposite directions at the same time.
Whoa, so the total difference could be huge.
It can be massive. People often quote needing tolerance up to maybe 5600 ppm total instantaneous difference. This demands extremely robust, high-performance CDRs, probably larger elastic buffers, and really thorough testing to make sure it works reliably. The STP symbol rate might also be higher, which could have a tiny impact on effective bandwidth or latency.
Wow. So SRIS offers flexibility but pushes the PHY design to its absolute limit.
Pretty much. It reflects a trend. Simplify the system hardware, like clock routing, even if it means making the silicon components, the PHYs, much smarter and more complex.
So choosing the clocking really is a fundamental system trade-off. Cost, complexity, EMI needs, PHY capabilities, it all plays in. Fascinating.
It's a critical decision early in the design process.
Well, this has been an incredibly enlightening deep dive, seriously unpacking the electrical nitty-gritty of PCIe. We've gone from encoding bits with 8B, 10B, or PM4 through differential signaling's noise cancellation,
to the constant battle against channel loss using ever smarter equalization, both TX and RX.
navigating the LTSSM states, balancing power and latency with the L states, and finally wrangling those reference clocks with different architectures.
It's amazing how all these pieces have evolved really in lockstep to deliver these incredible speed increases generation after generation.
Yeah, the key themes really stand out, don't they? Differential signaling is just fundamental. Signal conditioning gets exponentially harder with speed. Power versus latency is a constant balancing act. And clocking offers flexibility but comes with its own set of tough challenges.
And none of it works without those incredibly detailed specs and rigorous testing that ensure a graphics card from vendor A can actually talk to a motherboard from vendor B. Interoperability is king.
Absolutely. And it's not stopping. PCIe 7.0 is already being defined, targeting, 128 GTs?
128 GTs, likely still using PM4, but demanding even more innovation and equalization, maybe channel materials, connectors, who knows what else.
It just boggles the mind. Which leads to a final thought for you, the listener, to chew on. We talked about this incredibly complex electrical ballet happening billions of times a second inside our devices just to move data.
So thinking ahead, what other fundamental shifts, maybe beyond just refining equalization or PAM signaling, might be needed to keep pushing these data transfer speeds even higher? What new physics or perhaps new materials or architectures will engineers have to wrestle with to maintain that balance between raw performance, crucial power efficiency, and the absolute necessity of signal integrity in the future of high-speed communication?